Okay, I will turn this over to Richard, VK2ARH or slant W5ARH, and let him get us started. Thank you, Richard.
Thank you, folks, and thanks for coming. Thanks for coming on. And look, this has come together. It's been a lot of fun trying to bring it together, and you know, a big thanks. Mike's been involved in that as well. Dave's helped, and we've managed to put what I think is a great program together. And I hope you're enjoying it as much as, or will enjoy it as much as we did on the way through. So if we look at what I'm going to try and do today, this is the first of potentially 3 activities for the club involving the NFED Half Wave as project number 1 of the 23 Buildathon. Tonight, we're going to go through a presentation. The details of what I hope to cover is on the screen there. Saturday, as Dave mentioned, we'll be doing the construction day. And I really hope we do get to the, what I call there, shortly thereafter, the keen and enthusiastic is some of us that are familiar will go out, we'll actually erect the antenna, we'll help you tune it, show you what to look for, and hopefully we'll have some QSOs, and maybe we might even do a POTA activation or something whilst we're actually doing that. Turn that into a fun event in itself. And the other thing too is that this particular project will link in with the other projects that we do. So as we go through and build a little transmitter and all the other bits and pieces, you'll be able to use this antenna as part of that. And you'll have quite a capable antenna, which I'm hopefully going to convince you of during the next few slides. Before we kick off today, I just really want to try and set the scene for what today is about. It is about giving you practical suggestions about how to make this project a success, and tell you a little bit about the antenna and try and pull together all the information that is out there about NFED half waves. It's not a detailed technical presentation about every single practical element of an NFED half wave. As I started to pull this stuff together, I spent hours squirreling down this particular hole. My colleague over here on my left sent me a whole stack of technical information about the methods of calculating the required antenna width, et cetera, et cetera. You really can get buried into a lot of the detail, and it's a lot of fun following it through. So if nothing else, at least what we pulled together today may well give you an opportunity, or at least the encouragement to go and do some further research and understand a little bit more, not only about this antenna, but other antennas as we go through. One of the questions, the point I've made down the bottom there, remember, every single antenna is a compromise of something. And but this one I really enjoy, and I think it's a great one to do. So why did we pick this? You know, what were the basic principles that we're looking to do? We wanted a kit, a project that was going to be inexpensive for people to participate in. It needed to be easy to build and also provide a few opportunities to learn for those that have not actually done this sort of stuff before, about construction techniques, about soldering, et cetera, et cetera. But more importantly, we wanted at the end of it for you to have something that can be practically used within your ham radio activity. The idea was to have fun. But why did we choose the NFED half wave? What were the primary topics of discussion, if you will, that we went through? It needed to be easily deployed. It's a multi-band antenna. So those of you that get involved in HF, and that's where I spent most of my ham radio activities, in the HF bands, it's a great place to be, and having to swap antennas is painful. Here you've got a very practical antenna that can use on multiple bands. Flexible in its use, it's capable itself, and it doesn't need a separate tuner or a separate counterpoise. Now, when I say it works well, I've got a couple of examples here, and some of you have already seen this, but I wanted to share them for those that haven't. Even with low power, particularly using digital modes, you can get a lot of fun and a lot of DX activity out of this. By the way, just to put it in context, you can see on the screen there, this is actually the antenna I've got. This little couch here. That was one of the ones that I built. It's by Jason, KM4ACK. That's his portable NFED antenna. And that's one of the ones that I threw up over just before Christmas back in Australia. And you can see operating from home there, I'm being spotted all across the Pacific on 40 meters. We worked quite a number of stations in Japan, New Caledonia, across the Pacific. And then similarly on 20 meters, I'm not sure how clear that is. Yeah, you can see worked a whole stack of European stations. And, you know, that's a long way. That's the other end of the earth to those locations. And it's not really that large, but you know, you can see there's a massive number of end countries that we've worked. So even though it's a piece of wire and we've only got a few watts going up, it can be a very effective antenna. And if I just go back to the previous slide, I want to make the point that this is actually not under tremendously good band conditions. The time this was done, you can see here, The conditions at night were fair on 40 meters, so it wasn't good or excellent. This was just everyday sort of conditions. So correctly deployed, correctly built, the end-fed half-wave can be a very effective antenna. We made the decision to look at building a field deployable or a portable end-fed half-wave. And there's a number of options that we looked at and all the way around. And the ones that we've chosen are pretty much the ones that you can see on here. It's these two kits here for those that have seen the details. This is option 3, this is option 2. And ultimately, you'll end up with, if you're building either of those, a little pack. You can wind the halyard around, you can wind the antenna around, and you've got a really nice little portable antenna. Fits very easily in a little bag that you can just throw in your vehicle or wherever you want to do and head off out. We also have a couple of options. This is option, that's option 1, which is this little fellow here, which is an absolutely fantastic QRP Unun. And I'll talk a little bit about the differences in power handling and so forth with those as we work our way through. And there's also another option 4, which I'll talk about a little bit later in the pack. The reality is that the techniques that we learn building the portable one can be just as easily applied to a fixed installation one that you may want to put at home. So if you want to beef it up, put a larger toroid, further diameter windings, etc., you can create a very substantive half-wave, end-fed half-wave Unun that you could mount at home in a more permanent location rather than just having as a portable. And just to give you an idea, that you can buy a commercial unit if you want to, and you can pay $275 for it, pre-built. The ARRL kit you can see here contains all the elements. That's a $79 kit. This one here, which is actually sitting in that box there, was one I built for field day last year, and that cost me about $40. So permanent installations, that's the sort of money. That's everything. Okay, I've probably got enough washers to make about 50 of them when you work your way through. But certainly what I'm saying is, even at a fixed installation, it's a relatively inexpensive antenna to buy. The kits that we put together, I'll talk about in more detail as we get toward the end of the presentation. They range from about $7 up to $12, depending how many toroids you've got. Mate, they're an absolute bargain if you want to try and get one of those. If you haven't got your name down for one, we've got a couple of spares that people will be able to take home. And I'd buy it just to have the fun putting the thing together. They're that good. So look, let's talk about some basic construct and theory. We are going to get into a bit more techo detail as we work our way through. The heart of an end-fed half-wave, apart from the piece of wire itself, is the Unun. That's the unbalanced to unbalanced transformer that we need to be able to match the transmission line to the antenna. It's generally built with a 1:7 turns ratio, or either at a 2:14 or a 3:21. It effectively, all its role is to do is to match that 50 ohm transmission line to the actual antenna. Now, the kit that we're going to be building this weekend, there is a great video on the internet. Just click this link here, and I'm sorry, I must apologize to the guy. I can't remember the name. Got a further link coming down. But by the way, this presentation will be put up on the group's IO page, so you'll be able to see it and get the detail and so forth from there as we go. The reality is that whichever way you look at it, the end-fed half-wave really is a very good practical antenna, but knowing a little bit about it and understanding its limitations and how best to deploy it will really help everybody get the benefit out of it. So strap yourselves in. We're going to go into a little bit of theory and cover off on some of the discussion topics that we'll find around the place when we start to look at the end-fed. So if we look at how it works, the idea is it really is a half-wave piece of wire, very similar to a dipole in the sense that the only difference is dipole is fed from the center with a transmission line impedance of about 72 ohms. Now, if you move the feed point from the center of the dipole down to the end, the impedance of that feed point builds up to 2,450 ohms. So you need the matching transformer, the Unun, to actually take you across that, to make that match, if you will. Important thing to note for a bit later discussion is if you look at the end-fed half-wave, the voltage and antenna distribution across that antenna remains the same on an end-fed half-wave. You have peaks of voltage at the ends, and then when you come, which effectively, and I'll talk about how high that voltage gets, but also you have the current follows exactly the same path. So with a dipole, when you throw it up a tree or whatever, it's usually deployed either horizontally or as an inverted V. But the reality is the center of the dipole is the highest point of the antenna. And that's simply because the most amount of radiation occurs from the center where the largest amount of current. Yep, he's playing with the light, where the largest amount of current is. And we get exactly the same situation with the end-fed half wave. Now, also, because it's multi-band, the impact is that as you go up the frequency, you get more and more wavelengths, if you will, across that same piece of antenna. And that little graphic there is showing you how many wavelengths you get on the various frequency bands as it cycles through, and you can see them increasing as it works its way along. So if we look at that diagrammatically, we can see here, in our case, we're building an antenna for 40 meters. At 40 meters, we've effectively got a half wavelength. At 20 meters, we've got a full wavelength. 15 meters, we're going to get 1.5 wavelengths, and at 10 meters, we'll get 2 wavelengths across that particular piece of wire. The reality is that we really have multipliers of the fundamental frequency at the various bands. And therefore, it's important when you're balancing it, or when you're tuning it, if you will, that you choose to tune the resonant point that you want. So here, what I've done is shown by way of an example that on the top area here, if you choose a fundamental frequency of 7 megahertz, which is going to be down the very bottom of the 40 meter band, at 2 times the fundamental, it's going to be exactly at 14, then 21 and 28 as you work up through the bands. But if you've tuned the base of your antenna to, let's say you want to optimize it for FT8 on 40 meters, as you go up and multiply those number of times the fundamental frequency, the distance into the band is going to be multiplied. That makes sense? So you can see here, 7.04 becomes 14.148, 21.22, 28.29. So you move further and further into the band. So, part of designing it and tuning it for the way you want to operate is to choose where you want to optimize your antenna for, if you will, along that band. Unless, of course, you then start getting into the stage where you make adjustments, the electrical characteristics of the half wave, and I'll talk to those, so that you can, as the frequency goes up, you can bring other effects into play, which will actually push the center frequency back down to where you want it to resonate most optimally within the bands that you're actually working on. So when we start to talk about end-fed half waves, if you've been on the internet, you've seen the discussion, guys talk over breakfast, issues about you need to put a compensating coil in. Have you got a counterpoise? Do you need to be grounding it? What are common mode currents and how do they impact the use of the thing? What about a loading coil? Can we put one of those? And most importantly, safety considerations. So I'm going to try and summarize these for you in a practical way in terms of what it means for the end-fed half wave. Let's talk firstly about the compensation coil. Some of the commercial units that you see will be sold with a compensating coil. And what it is simply the wire wrapped around some form of former, which effectively acts as an inductor. So as the frequency changes, the effect of the inductor impacts the relative length of it, let's just keep it simple, of the antenna, and it effectively changes the resonant point, the lowest point of resonance on each of the bands. So as the frequency increases, it will actually bring back the resonant point, or the lowest point of the lowest SWR point to achieve where you're achieving best resonance on that frequency, and brings it closer and closer. And you can see this is an example here from a presentation that Steve Dick did, where he's saying that this particular type of thing here, which is a 1.5 microhenry inductor, 6 turns on a 1.25 millimeter outer diameter piece of PVC, lowers the resonant frequency by those factors you can see in there, 22 kilohertz at 80 meters. By the time you got up to 10 meters, it's actually lowered it down by 1 megahertz. So if you optimize your 80 meter antenna, in this case, for the middle of the voice band or at the lower end of the voice band, as you go up, the multiplying effect is reduced and it tends to keep it down toward the point where you'd actually want it within the band. Does that make sense? However, this gentleman, I can pronounce his surname, Mike Miladovsky, W5ARH, who is very enthusiastic about the antenna, did a great job modeling the characteristics of the antenna across all sorts of variations and so forth. And I really do encourage you, if you really want to understand the theory as to what's going on, to have a look at that YouTube video that's there. He argues very persuasively that building a compensating mechanism, if you will, in the antenna is best done not using an inductor, but by using a capacitor and a resistor combination, which you can see there in the bottom right-hand corner. He argues that on the basis that using a capacitor and resistor is far more precise in terms of the electrical characteristics that the thing creates when you put an AC signal into it, and therefore you can get a much more accurate outcome. And as said, he used it to model it, and his situation there uses a 200 picofarad 50-volt silver microcapacitor and a 32K 2-watt leader resistor, and he just puts that in line. Now, subsequent to reading that article, I've gone out and bought some of those, and I'll be trialing that, if you will. But the impact you can see is down. I haven't had time to build it yet. I only got back on Sunday. Down in the bottom right-hand corner there, you can see the, we bring it down here, you can see the original antenna, and you can see that as you move further away, the lowest point of, the lowest SWR point, if you will, in each of those bands moves further and further away from the baseline. By building the antenna this way, you can see it's actually moved every single one of the, although the 10-meter one is probably down a little bit to the left, it's moved it all along and it's done it very nicely. So if that is important to you, you can add either a compensating inductor or a compensating capacitor circuit, if you will, in order to do that. You don't have to do that. Let me say that. I mean, all the stuff that I was doing before, those contacts that I showed you, was done without either of those. It was just using the bare bone wire, which I'd optimized for the particular frequency that I wanted to use it on. The other thing to talk about is the compensating capacitor. Now, I don't want to, sorry, we've just been talking about a compensating capacitor and resistor network. Here we're talking about the input capacitor, which has an impact on lowering the SWR at the higher frequencies. Now you can see here that that fits in the circuit, and on all of the kits, that's a little tiny capacitor that's sitting down the bottom there. It generally goes between the ground and the input on the small end of the turns, if you will, on the left-hand side. And you can see the impact that that has on the SWR at higher frequencies. So here, without that capacitor, as you can see, as the frequency increases, the SWR across the various bands increases, but by putting that capacitor in, it drops the SWR at those resonant points across that curve. So a great way to solve that problem. And there's nothing too fancy about it. That's simply a 100 picofarad capacitor. The voltage rating I'll talk about in a bit, but generally the ones that you've got in the kits are between 3,000 and 4,000 volt ratings, or if you've got the mega ones that Dave has, 10,000 volt. I don't know how much power he's planning to put in that thing if he's going to have a 10 kV rated thing there. A couple of things to note.
Dream big. Just dream big.
Dream big.
Yeah.
I can just imagine the impact of all the common mode current would emanate from that. Quick technique there, if you find yourself building one and you don't have a capacitor that goes quite up to that voltage, if you double the capacitance and put them in series, you'll actually double the voltage rating. So 200 picofarad capacitors in series will allow you to increase the voltage handling capability of that antenna. Let's talk a little bit about the radiation patterns. You know, there's a lot of detail contained in those charts down in the lower right-hand area of the slide there. The reality is, think of the end-fed half wave as radiating in a manner which is very similar to a dipole. Now, very rarely does a dipole sit up in free space, and you get that, you know, the theoretical pattern where you get the two lobes and the two side profile lobes running out. The reality is, as you move the dipole up and down, closer to the ground, further away from the ground, you ever seen the computer modeling software, you get signals bouncing all over the place, reinforcing one another, and you start to get, as you can see down here, the higher you go in terms of wavelength, the more lobes you tend to get from that. And the reason why you can't always say, well, what's going to be the radiation pattern from the antenna, if you deploy it as an L, as a zigzag, or whatever, there's lots of ways you can do it, that is going to impact the radiation pattern that you get from the antenna. The one thing that I would say is that if you think of it as giving you roughly a 2.2 dB gain, if you need a number, just think of that one. Everything else is going to be a variation from that depending upon what you do. And you do get a degree of directionality if you use a sloper. And that directionality tends to bring the lobes more around to the direction of the slope rather than being parallel to each of them. But as you can see, at 40 foot above the ground, that's a fair way up. At 10 meters, you've got lobes going every which direction. So you should be able to pick something up coming from somewhere or communicate effectively with that. But in case anybody wanted to know, that's the radiation pattern that you get from them. Remember I said that the best way to deploy the antenna is to ensure that the center area where you've got the maximum amount of current, i.e. the maximum amount of radiated energy, is to get the center of the NFED up as high as you can. And here's just a few techniques that tend to be used. My own preference is I tend to go for the sloper in the top right-hand side there. That's the way I've deployed it at home. Toss a piece of rope up over a tree, pull the thing up. So it's simply one halyard, if you will, to pull the antenna up and anchor the point down fairly close to the house or wherever you want to do it. But you've got a fair amount of flexibility. I think that the second best way is often to use, shown here in the bottom right, up over a branch and down, because you've effectively achieved the same thing. You've got the highest radiating component of the antenna up as high as possible, if you will.
Wasn't that your configuration at field A, the lower right?
No, it was the top right.
The top right?
Yeah. I'm sorry, you are right. It went up over a limb and then probably down about another 10 feet or something on the other side. If you've got the ability, you can string it up vertical and it's going to act like a vertical antenna. Yeah, that's the easy way to do it. It's such a flexible antenna and it's so light and easy to adjust.
So on field day, because I remember I was working with you, I remember standing on the roof of my car to pull the thing down. So you had the center of the antenna like at the top of the tree. Is that how it is? Because you said you wanted that to be the highest point on the wire, right?
Yeah, so it went over a branch.
Okay. So you're the center of the antenna wire on top of the branch, like sitting on the branch?
Yeah.
Okay.
But my preference would have been, if I could get a tree far enough up away and high enough, my own personal preference is to use the one on the top right, the sloper. Right. Because effectively, the
feed point is at the high spot.
The feed point, the advantage of the NFED halfway by comparison to a dipole, for example, is the feed point is often down low. Mm-hmm. So you get nice and close to your radio. You don't have to also then worry, you also don't have any weight to speak of, if you will, out in the middle. So you're not having to support the center of if you think of a dipole, you have to have a halyard to put the center up, and then you're going to have some way to secure each end. So you've usually got 3 halyards, and this thing works just as well. And what's more, a dipole is usually a single band, whereas this one you can operate across multiple bands. Look, you tell I've got a love affair with this thing, but it really is a very favourite antenna of mine, as I said there. Look, a couple of points there. Don't deploy the antenna with more than a 90-degree bend on it. So you can, if you've got a limited area, you can run it out and then over this way and that way to actually fit it into the area that you've got. But you shouldn't have a bend in it that's more than 90 degrees, because you start to get the thing folding back on itself and it starts to impact its resonance.
So that V configuration, that angle would have to be greater than 90? Ideally,
yes. And so similarly, when you have the inverted L, which you can see up here, don't have a half-hearted inverted L. Don't bring it back down so that the angle between the two is less than 90 degrees. You've got to get that further one up into the air if you want to optimize what's actually going on. The other thing is that when you need to tune it, you can actually fold the antenna back on itself and wrap it around. So you don't need to be cutting it, if you will, so that if like me, you want to work digital at one particular point and then you want to optimize it and you want to move it up to the voice area, you can just drop the end down, lengthen a little bit, just wrap it back up and put it back up the tree or wherever you want to do that. it's really important that I mention this stuff about safety associated with these things. I indicated to you before that when you move the feed point down to the end of the antenna, the impedance goes up, but you also then have the antenna where you have the highest amount of voltage distributed across that piece of wire. But in the case of, and that's the same for a dipole, whatever it is, I mean, it's going to be the same. But the difference now is, you may recall, we've just gone and put a matching unit in there. So we've added effectively a matching transformer with a 1:7 transformer ratio. So the voltage that is exhibited at that particular point is now multiplied by 7. So if you look at so that high voltage now exists because it's gone up by 7 at the feed point and also at the far end of the antenna. How much has it gone up? What's the values? Well, a lot. I mean, if you look at it here, you look at the power that's been put into the antenna, even at 10 watts, right? That normally has a RMS voltage of 22 volts, peak, so the output voltage of that 7 times that becomes 156 volts. So the peak voltage is 222 volts on a 10 watt input signal into that antenna. By the time, significant. By the time you get into 100, you've now got a 700 volt thing. Now, I mean, it's not 700 volts like it's coming out, because there's not a lot of housing to it, right? But I certainly wouldn't want to be touching it on the way through.
That's fine.
You'll just straighten your arm out.
It'll straighten a few other things out too. So you can also see here that if you happen to be a Dave who wants to put wants to put his 10,000 volt capacitor to good use, you're getting up to some serious voltage. The bottom line is, the reality is, you need to practice electrical safety associated with the feed point. So whilst ideally you would put the feed point as low as you could to maximize the vertical plane, if you will, when you run the antenna out, it needs to be out of the way where little fingers can touch it or what have you. Just be conscious of the fact that you're going to have, sitting at that antenna point, when you're going to have there potentially, let's say you're running 100 watts in there, you're going to have what, a 700 volt zap if you're going to touch it. So be very, very aware of that as we go forward. One of the techniques that can be used with these is to extend the wavelength, extend the length of the antenna, the frequency range that you're able to use it on, by putting a loading coil in there. Now, I'm not going to go into this in a great level of detail, but you can see here, for example, that if you have the 40-meter antenna that we're building, you can extend it to run to 80 meters by just simply adding another 2.5 meters of wire at the end, but putting a coil, a loading coil, if you will, in the end. So you don't end up having to have a 132-foot antenna. You can have effectively, I'm going to have to convert it to feet for you guys. Trust me, 2.5 meters, what's that? 7 feet, 7.5 feet extra, instead of an extra 66 feet by putting the loading coil in. And, I won't go into it here, but here's a couple of examples as to where it's been done. Here's a nice big fat one on this. If you look this guy's site up, you'll be able to see it. And this is Hayden, VK2ARH, where he built on one of his YouTube videos, VK4YE design. I don't know why he did it this way. I mean, you've got all this extra weight sitting there with those 2 insulators. I don't know why he didn't use the PVC thing itself and secured it to that. Would have made a neater solution in my mind, but I'll leave it to him as to why he chose to do that.
PVC melted.
Yeah, well, Dave isn't allowed to use this one because he'll melt it, right?
Now, do you use stranded or solid
for the wire? I will come to that, right? As we work our way through. A lot of debate about whether you should put a counterpoise on an end-fed half-wave antenna. The reality is, and the short answer is, you don't need to, because the coax itself becomes the counterpoise. Now, that comes with it some advantages and some disadvantages. The reality is that depending upon the length of your coax and the extent to which you're operating off the resonance of the antenna, you may or may not get common mode current flowing down the outside of the coax of the antenna and creating problems for your rig. And I've had end-fed half waves. In fact, the ones that I showed you with all the stuff there were operating without any form of choke. But I've also had other ones where I was practicing and trying where I had problems with common mode current coming back down the coax. If you do want to install a counterpoise, which often helps and reduces the amount of current, the recommendation is that you only need one which is 0.05 of a wavelength of the antenna that you want, the frequency in which you want it to operate. Now, if we look at chokes, I mean, most people don't. Sorry, who uses an RF choke on their? Okay, yep, some do, some don't. I managed to buy my first one about several months ago when I had a few problems with that, but they do make a huge difference. So if you are experiencing problems with that, you can go and buy one. But more easily, you can very simply make one. And here is, sorry. And by the way, in the bottom left-hand corner here, the research that is here basically said that if you're using a coax length of 45 or 50 feet or 20 feet, under certain circumstances, you don't actually need a choke because the situation that I described comes into play and you don't need it. My coax is actually 50 foot long, so that's probably why I didn't need to do it.
That Mike guy that you referenced earlier, I think he made a comment in his video that he was running half of his coax laying on the ground,
Yes.
which in effect became a common mode choke.
Yes, he did.
So it all depends on your installation.
It does, but look, the reality, the safest thing is to make a choke and to use one, so you're not going to have that problem. And I'm just showing here, there's a couple of examples as to how you can do that, and I've got some more details on the next slide. This is a 10-turn choke, this is a 15-turn choke, and by the way, if you're winding, and that's around a FT240-43 or 52, depending which one you do, and the data that I'll show on the next slide actually has 17 turns, but the reality is you can't wind RG58 more than 17 turns around that coax because you actually fill the inside of it, if you will. The other thing is that putting beading on the coax like this is often a solution that's offered, and you can buy those beads. Like for like, it's much more expensive to do that than it is to simply buy a toroid and wind it working its way around. And the toroid actually offers double the choking capacity, if you will, think of it that way. It offers double the reactance than the beads do. So it's much more effective to do that. And you can see here, that's simply winding the coax around with a couple of zip ties and just having it sitting there, and it works its way through. In terms of, here's a good example where you could actually, rather than just having it sitting there on the coax, you can actually mount it inside a box and do whichever way you like. Here's a lot of research. G3TXQ has made a great contribution to the hobby by doing a lot of research on the effectiveness of chokes with various formers, various number of turns, different insides and what have you. And the recommendation here based on all that is if you're going to make one, do 12 turns of RG58 on an FT240-3. That's going to give you tremendous choking ability across the entire band from just below 5 megahertz all the way up to the HF. If you really want to focus on 80 meters and 160 meters, use one of the other options that are shown on here. But the sweet spot is really to have the situation, where you have a higher resistive choke than a reactive choke, and the zones in which that occurs is the black line that's shown along here. So this particular variant, which is the same one that has been built here, which is the 12 turns of RG58 on one of these guys, provides a really good broad frequency RF choke for use.
Is the FT240-31, is that the toroid or?
Yes, I'm sorry.
Okay.
So the toroids, and I'll talk about toroids in a little bit, but just briefly explain, the first digits, like the FT240, means it's a 2.4 inch, right? A 140 is 1.4 inch. The dash number, 31, 43, 52, whatever it is the composition of the material that the toroid is made of. It has different characteristics. Some is more effective at different frequencies and what have you. The contrast that's drawn here is between the dash 32 and the dash 43, and the dash 31 is more effective at the lower frequency range, and the dash 43 is like middle of the road. If you go up to 52, becomes more effective in the higher frequencies, but less effective in the lower. So the advice here, feel free to go and research it yourself, but I love this bit of thing. And if I didn't spend 10 hours researching different chokes and options and bits and pieces, and then deciding which choke I was going to build and where I was going to put it, was there. And this is the result of my research. So that if you want to build an RG58, 12 turns wrapped around a 240 toroid, you won't go wrong.
If we take the HDMI cable and run it 3 times around that, and interference on the screen.
Beyond my competency level. All right. I really do encourage you to watch Mike's video. He has this wonderful expression where he gets excited about the things and he works his way through, and at the end he announces, "What's not to like about that?" This was his what I describe as almost perfect end-fed half-wave situation. This is what I want to build for my next project, which has the compensating capacitor there in the middle, which is going to bring all of the frequencies as we go up through the multiples back into the sweet spot for each of the bands. And then it has a common mode choke. And he actually, I watched this after I'd done all the research on the choke, similarly proposed the 12 turns on the 240. But his modeling software says that needs to be 12.33 feet from the feed point of the Unum to get what really is a fantastic match across the higher band. So that's going to be my experimental fun as we go forward here. And yep, so I encourage you to watch that video. So look, that's a lot of discussion about chokes and whether you should ground. So we didn't get onto whether you should ground, compensating cores and what have you. Let's pull it all together here in terms of what it practically means for what we need to do to build the end-fed half-wave. And I grabbed the base slide here from Steve Dick's presentation. If you find that on the internet, it's a great presentation. By all means, have a read. So the reality is the choke balun, if you will, for the CMC is optional, but it does allow the counterpoise length to be used in the coax without impacting the radio. So the common mode choke that we spoke about through there, he says here it should be installed near the rig, never near the Unum. And the reason for that is if you install it near the Unum, you've actually destroyed your ability to use the counterpoise because the choke is going to prevent any traffic, if you will, up and down the outer of the coax. So move it down, put it more toward the rig.
Does introducing the choke into the system negate the need for the specific length of feed line?
Yes.
Okay. But it still needs to be enough to space the choke away from the...
That's correct. Yeah. Compensation coil or compensation inductor, if you will, only use that if SSB is your preferred mode and you want to have the freedom to use SSB without any form of balance, tuner or what have you on each of the frequencies. If you're like me and you love using digital, you can align it down to the bottom end of the band, and by the time you've got your multipliers, you're still within a usable range, if you will, of the antenna in some of the higher bands. Counterpoise is optional, but it will reduce the common mode current on the outer of the coax if you choose to use it. Grounding is not required, but it is recommended as a safety practice for a permanent installation from lightning strikes and the like, if you will, on the way through. So I've just added the comments in blue there from the work that I did. And remember, from an inverted L position, get the antenna up as high as you possibly can in the center. So in the last few minutes, so let's turn to the project itself. Hopefully we've covered, give you a bit of an idea of the background to the antenna. Let's get down to some practical build realities. I indicated before that we talk a little bit about toroids. I'm not going to go into a great deal of detail here, but all toroids are not created equally. There's two guys here. Steve Dix provided some information in the top right-hand corner, and where's his call sign? Mike 0 Oscar Papa X-ray. Did a lot of good work testing out the various performance of different winding ratios, different toroids and so forth, and you can see the results here. But again, as I said, we don't live in a perfect world, and sometimes we have to compromise one thing or another on the way through. His two recommendations with all the research that he did was that if you want QRP using this particular ferrite here, and it's not actually listed as an FT0 62, I should say dash 43, not 42, is a super efficient toroid. This thing will generate an on efficiency well over 90%, or certainly over 90%. That's the one that we're showing down through here. So if you're going to use QRP operations, obviously the best thing to do is to not waste heat, or not use your antenna signal to generate heat in the toroid. So this is a little favorite of mine, and it really is a nice needle build. Now that's option one for the folks who selected option one of the kit options. One of the toroids that we didn't run with, and where's yours, Mark? Here we go. Is I call this the fat boy. It's probably politically incorrect for me to say that.
I resemble that.
Yeah, I used to.
Stick around the edges.
That's right. That's right. It's nice and cuddly. This is a very thick toroid, as you can see here. It's about 1.4 mil. In fact, it's it's 1.54 inches in diameter, but it's a thick, chunky toroid. And but that is a very efficient one. You know, around the 90% mark in terms of its efficiency. It is a little bit difficult to wind, and probably for a first project, it may not necessarily be a great one. But you know, you're more than welcome to go and do that. We ultimately selected a further two options, which was the FT140-43, which is shown sitting in here. It fits very nicely into both this and the smaller. Actually, you've gone and used a 114. That one. This is much better. as in the FT140 toroid will give you a better efficiency than the 114. So and that's what we've got for everybody who selected their kits. So for example, with 3, so the kits have the FT140-43 sitting in there. And then for option 4, which was the final one we chose, actually got a collection of the FT124s, which is the same one that Jason has used in this kit. And I know from personal experience this works extremely well and provides good results. And that's available for anyone who ordered and wanted option 4, which is that one there. So that has the FT124 toroid that's in there. Now, if anybody didn't buy a kit or didn't book one, we've got about a very small number of ones available.
Option 3.
You'll take an option 3. Hang on, they need to talk to Mark afterwards. Right?
Which one was option 3?
Option 3 was
That's a bad one.
was this one with the FT140, and I think there might have been one of those left, and you probably just grabbed the last one. To be honest, how much are they? $8 or something for
The option 3 is
option 4s?
Option 4 was $8.
$8. That's the bargain of the century, right? I mean, we've pulled that together from parts from all over the place with freight and shipping and tax, and pulling it all. I mean, you wouldn't be able to build that for 3 times that amount if you wanted to do it on your own. So I thoroughly encourage you to get hold of one of those. Should have put this slide up. That shows you the various options that we've got. By the way, the QRP option here, which is really not, I'm almost in love with this little thing. That's a 3:21 ratio and turns ratio on here. If you are not dexterous, you don't have a high degree of dexterity, don't try and wind this toroid as your first go. Get somebody else to do it. But the option 1, we actually also, no, we've got one option. There's 2 option 1 kits left.
Okay, I want one of those.
We've got one option kit, 1 left. This actually is a pretty neat, this is a little hub put together by
DL2MAN.
No, it's another German ham, and I'm going to be DG1JAN. He actually cleverly designed that. I don't know if you can, actually, let me see if I can find a, there is a kit that I'm looking for. He actually has a system on that, so you can, depending which jumper you connect and where you actually connect the wires into it, it can either be a 1-to-1, 1-to-4, or 1-to-49 transformer, which means it can either be a common mode choke, you can use it for a off-center fed dipole, or you can use it for an end-fed half wave. So a very flexible little and very which is that's actually mounted on that one using the same thing there. But as I said, different toroids give you different characteristics and frequencies, different efficiency ratings on the way through. We chose this one, QRP Plus, and that's good for about 60 watt sideband because of its ease of use and the ability to wind the toroid easily. And it's a good balance, if you will, between ease of construction. The advantage, of course, is once you've wound one of these things, it becomes addictive. And I started out winding one, and I've got 1, 2, 3, 4, 5. By the way, I'm happy to do a deal on a pre-constructed one. If anybody, I don't know what I'm going to do with that many elements as we go through, but a lot of fun. A couple of things on magnetic wire, or magnet wire, if you will, when you wrap it around. All magnet wire, just like toroids, is not created equally. Different, you need to use, basically, the more power you put through the device, the higher the thicker, greater thickness that you need on the wire. And also consider looking at the temperature rating of the wire. Now, you can see I used all my 18 gauge, if you will, for the kits, or what was left of it. 22 gauge here, which is what we've used for the non options 1 and 4 are using this particular gauge wire here. This is rated. You can see here most. In fact, I think the next slide. Do I have it? No. Oh, sorry, it's here. Most of the enamel wire generally has an indication of the temperature at which the enamel is going to melt. Now, the cheapest stuff around, the easiest stuff you can see and buy, comes in at 155 degrees Celsius before it actually breaks down, and you don't want that to actually occur. Now, the reality is, if you've got a toroid that's running at 5 degrees Celsius, I think you've got more of a problem than just the enamel melting on the wire. Most toroids will actually break down at around 200 degrees up. They only rate them at 200 degrees Celsius. You guys don't know what a Celsius is.
Sure we do.
You do? You do? All right.
It's on my calculator.
Okay. But, look, the reality is 155 is going to work fine, because if you're going to get up to that temperature, you've got more of a problem than just that. But the reality is, if you do have the option of buying the higher temperature rated outer, by all means, go ahead and do that. And the bottom line is, the more you go up in power, the thicker the wire needs to be for the efficiency of the toroid. Also, antenna wire is not created equal either, and I said I'd come back to antenna wire. Consider the power handling requirements. Whether you use multi-stranded, whether you use hard-drawn copper wire, is really going to depend upon how you want to use it. And some of the considerations that I think you should look at here, I've laid down there. The power handling, increase the thickness of the gauge. The durability, consider whether you've got a UV protective outer or not on the wire, and whether or not it's going to be dragged up over trees. So Mark, has very kindly supplied, dare I use that expression, some antenna wire for those that are building the kits on Saturday. This is 22 gauge Teflon coated wire, very flexible, fits beautifully around the whatever hub you want to use. And by the way, guess who's got a 3D printer? Right, there's all sorts of designs on there, and this is exactly the same hub. You can see that.
And we're hoping that for those of you in apartments, that it will be very stealthy. Right?
Yes, yeah. So I mean, the advantage. Well, even those of us that don't live in apartments, when they go home, don't necessarily want to advertise the fact that you've got an antenna running across.
Or
the
HOA.
To the best of nature.
That's right. So I actually had mine up for about 3 days before she noticed.
Before she told you she
Hang on, you're not recording this, are you? That's right. So, and look, the hard-drawn copper wire is great if you want a permanent installation for a long time, but it's not something you're going to pull up and drag down, because it can be brittle, if you will, when you work it around. So you need to consider the fact that what wind, how you affix it, in terms of how you protect it from movement of the tree, all those kind of things, whether you're going to be dragging it over a tree branch, and also consider the weight. I mean, the heavier the wire, the heavier the gauge, therefore the heavier the wire, smaller the gauge, the more it's going to weigh, and therefore all your hardware that you're using, the rope that you're securing it with, the attachment points and so forth, also increase in their requirement for it. So just consider all of those things there.
What do you think of copper-clad steel?
Good. The you mean steel-clad copper? Whatever.
Copper-clad steel.
Copper on the outside is what he means.
Thank you. Look, I've had a lot of success in my apartment with speaker wire, stripping it. You know, some of you have seen the pictures with the antenna running around the kitchen and all sorts of bits and pieces.
The big advantage of the copper-clad steel is it doesn't stretch like copper will.
Correct. Yeah, that's right. And in fact, my recommendation in terms of what you're looking at here, and I realised in packing I forgot to bring the two examples down. I use 18 gauge for my fixed installation when they're going to leave up for a long time. And that's the one that I used on field day. And then, in fact, that's 18 gauge here. And you can see there's a particular attachment technique that I'm using. I've got a little thimble that it wraps around with a clamp, for want of a better word, which takes the strain off on the antenna and then just feeds down into the end-fed half wave in the Unan down through here. 22 gauge is perfectly okay for portable operations. The advantage of that is it's very flexible, easy to deploy. And if you want to go and buy something that you know is going to last, I can thoroughly recommend the Poly-Stealth wire. That's sold at Ham Radio Outlet. It's several other locations in the US where you can get it. That is really tough copper-clad steel, if you will. but it's a multi-strand on the way through. It's not a single-strand wire, and that is, from memory, I think the 22 gauge has a breaking weight of about 75 kilos. Do your own conversion of pounds. And the 18 gauge is about 135 to 150 kilos. So, you know, that's even weighs more than me. So good wire, but I mean, a 66-foot length of that stuff's going to run you somewhere between about $18 and $22 for that length of wire to be able to do that. If you want to use speaker wire, that works just as fine as well. But of course, it's going to stretch a little bit more than the other stuff, and perhaps isn't as durable.
It will weather too.
And it will weather. As will, I mean, I imagine this would weather as well. I'm not sure what the UV protection on the black stuff is here.
It seems like Teflon, I think, isn't it?
It is Teflon, but I don't know what it's UV.
Yeah.
I mean, let's face it, we're building a portable antenna here, which you go out for a field day, whatever it is, you throw it up in a tree, you use it for whatever, day, 2 days, a couple of hours, fold it back up, take it home, and you're away. So look, the kits, as I indicated here, we made a number of winder choices available, whether you actually go for the H-style winder, which is going to end up with something like this, or you go for one of the smaller QRP portable type options on the way through. I mean, having said that, the option 4, if you want to pick one up and wave it around, that has the same toroid in as this here. I mean, that's good for 20 watts digital. Without any problem at all. I mean, I've used 20 watts digital quite successfully on that, and it didn't even melt the goo that I put around there to hold it in place, so it couldn't have got too hot. I wasn't going to go out and run and touch it to see how it was heating up on the way. In the kits, you've got the toroid, the magnet wire, the capacitor, zip ties. You've got all the bits and pieces you need to put the antenna together and have some fun. So I encourage you to do that. I set instructions. There's actually a picture as to how to wind the toroid, and for the option 1 kits there, we've got the little chart there that shows you where to connect the wires to and how to put the jumper on there if you want to convert it to one of the other style antennas. And at that cost, there should not be one left on here when we walk out the doors. They're a lot of fun. So look, lastly. There's a multiple ways you can connect your antenna. I mean, I'm sure you could talk it over breakfast for hours and hours in terms of which is the best technique as to how you're going to do it. Just wanted to point out a couple here. Actually, maybe let's go to the next one, which is probably a better way of doing it. You know, here it shows a number of examples as to how it's done. Here you can see there's a stainless steel nut with a wing nut connected with a crimp connector, which enables you to basically take the wing nut off, put the thing on, screw it back up, and you're away. This one here, perhaps a more permanent connection where you can see that's been looped around the hole in the hub, and then just putting a zip tie to hold the antenna there. and connecting it and soldering it into the part of the hub there. This one here has actually got a, I'm trying to think of the name of them, bullet connector. That's what I'm looking for here. So they've got a bullet connector there, so that their piece of wire is going to have this this bullet connector, and they're just going to stick it in there and work away with it. And then you can see now, and in fact, there's another example of how it's being used here. You can start to see now how your imagination can run away with you in terms of what's going to work for you, et cetera, et cetera. But we've made it easy for you. We've given you an option, so you can jump to that. So we're going to, in the kits, I've provided the hardware to enable this style of connection here. And in fact, I'll use that one, just show you here. So effectively, you've got the wing nut with the machine screw going through there, and there's a couple of connectors, one which will take the strain, and we'll show you how to do that on Saturday, and also the final endpoint. The advantage of that, of course, is if you wish to, you can keep the hub being stored separately from the wire. So as you work it out, and it's the same situation works with the H1. If you choose to do that, I think you might want to choose. You want to use this, or Mark's got undertaken some course in mountaineering, and has come up with all sorts of carabiners and connection points here. I think he's going to strap that to his belt. He's going to climb the top of the nearest mountain and then deploy it on. And look, please feel free to come up. We're just about finished here. Have a look at the various options that we've got here. This is again a connection that Dave built a number of years ago, I think, on the way through. You can see the different types there, so please feel free to have a look and work their way through. I should have flicked to the next slide. It's that long ago since I did. In fact, here's the YouTube that I was referring to that shows the Brazos Valley Amateur Radio Club did a build-a-thon, and they built this on their field day, I think, if you will. We're using exactly the same technique as these guys. So if you want to get a head start for Saturday, you want to go back and see how they built it. It's a good video and a great. In fact, this gentleman here, KI5NPL, ham radio for non-techies, has a YouTube channel, and one of his YouTubes is how to build that, which is very, very similar, you can see here, to what we're actually doing on this coming Saturday. So hopefully covered what I hope to in the agenda.